Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to solve one design example using direct design method. In fact, we are going to design a two-way slab system by using direct design method. The problem is, or the given data is, design a slab system having 3 panels of 6 meter span in north-south direction and 4 panels of 8 meter span in east-west direction. Story height is given 3.5 meter. Service live load is given 300 kg per meter square. Superimposed dead load is 350 kg per meter square. Specified compressive strength of concrete is 25 megapascal. Fy of reinforcement is yield strength of reinforcement is 420 megapascal. So there is no drop panel and column capital. So edge as well as interior beams are present in both the directions. So size of column is 375 by 375 millimeters. Size of long beam is in east-west direction and its size is 375 by 700 millimeter. And size of shorter beam spanning in north-south direction is 300 by 525 millimeter. So if we summarize the given data, so we have 3 panels of 6 meter in north-south direction, 4 panels of 8 meter in east-west direction, story height is given, live load is given, superimposed dead load. So superimposed dead load means dead load without the self weight of the slab, excluding the self weight of slab. So concrete strength is given, steel strength is given, column size is given, and size of east-west spanning beam is also given, and size of beam spanning in north-south direction is also given. And the information given is beam are present in all along the columns or between all columns. Okay, if we sketch that slab system, so it will be like this: 4 panels in this direction and 3 panels in this direction. So beam spanning in the longer direction, here it is 8 meters, so it is longer, and this 6 meter it is shorter. So in the direction of longer span we have B1 and B2, and these are long beams, and the beams in the shorter direction we have B3 and B4, and these are shorter beams. So if we check that how many different type of panels are available here, so this panel 1, which is a corner panel, have B1 and B3 at the edges and B4 and B2 at the interior spots. Similarly, this corner panel, this corner panel, and this corner panel. So these 4 corner panels are identical. Similarly, the next edge panel on the longer side, it is a second panel, so this and the adjacent panel, these both are identical. Similarly, on this side, these 2 panels are identical because we have same length of panels, 4 panels of 8 meter and 3 panels of 6 meters. So because of symmetry, we can say that these 2 panels and these 2 panels are identical. Similarly, this 3 panel and this 3 edge panel and this 4 panel, this 4 panel. So these are identical panels. So only we have 4 different panels. So we need to design these 4 panels to design this complete slab system. So as the spans are constant in both the directions, so for complete design of slab system, 4 panels 1, 2, 3 and 4 need to be designed. But in this example, we will solve only for panel 1. We will design this panel 1 because it is just an example to summarize or to just minimize the data or minimize the calculations. To shorten the calculations and the length of the video, we will solve just only panel 1. The first step for the design of slab is to select the thickness of slab. So to select the thickness of slab, we have a table given in ACI code, section 8.3 and table 8.3.1.2. Minimum thickness of non-prestressed two-way slab with beam spanning between all supports on all sides. So in our case, we have beams between all supports, so we will use this table. And according to this table, the value of minimum thickness is based on alpha F. And alpha F we have studied in the previous videos that it is the flexural stiffness ratio of beam to the flexural stiffness of slab. So at that moment we don't have the thickness of slab, so we cannot calculate the alpha value. So initially we need to assume some suitable value for alpha F. For example, we assume that the alpha F value is 2. are greater than 2 in our case. It's our assumption. And alpha FM is actually the average value of alpha F for all beams on edges of a panel. So what we will do, we will first select the panel 1, and for that panel we will consider the alpha M value greater than 2, and then select the thickness value from here. So either calculate by using this formula, and the value of this thickness should be more than 90 millimeter. So if the thickness from this formula comes out to be greater than 90, then it's okay. Otherwise, we need to consider this minimum value of 90. Similarly, we will check for the other panels, panel 2, panel 3 and panel 4, and we will select the highest value out of these four panels as a slab thickness. But as I said, in this video, I will solve only for panel 1. So I will show the calculations for panel 1 only. So assume alpha M is greater than 2. Why we have assumed? Because for calculation of alpha F, we need the thickness of slab. So initially its value is assumed to calculate the slab thickness, and later the thickness of slab is checked for shear and flexure. We will check whether the selected thickness is adequate for shear as well as for flexure, and we will also check whether our assumption is true or not. So the thickness value will be based on this formula, which is LNL 0.8 plus Fy over 1436 plus 9 beta. Here Ln is clear span in longer direction, and this beta is ratio of clear span in longer to shorter direction. So first of all, clear span in longer direction, so 8000, the center to center distance between the columns is 8 meters, so 8000 millimeter, and the size of the column is 375. So half of 375 from this side and half of 375 for this column. So we need to subtract that. So the total will be 375. So here we will get the clear span in the longer direction. Similarly, in shorter direction we have span 6000 millimeter, and again we need to subtract the width of column. Half width from one side and half width from one side. So total deduction will be equal to width of the column. So from here we can calculate the span in shorter and longer direction. Then we will take the ratio, which is beta, so longer over shorter. So this value comes out to be 1.35. Then substitute these values in this formula, 7625. Sorry, here it should be 7625. And 0.8 plus 420 for the concrete strength, 36 plus 9 and 1.35 is the beta value, and the minimum value of H is 174 and it is greater than 90, so it's okay. So we can either select the value 175 or some higher value. So say we consider it as a 180 millimeter. We have selected the higher, a little higher value. We also need to check for other panels, panel 2, panel 3 and panel 4. If the value for those panels, the minimum value for those panels is less than 180, then it is okay. Otherwise we have to consider the higher value. Okay, next step is to calculate the relative stiffness of beams. So in case of panel 1, we have 4 beams. B1 on this side, B2 on this side, B3 and B4 for panel 1. B1 and B2 are longer beams, B3 and B4 are smaller beams, and the size of B1 is 375 by 700 and B3 and B4 is 300 by 525, which is mentioned in the statement of the problem. Okay. So first of all, B1. So in case of B1, its span is 8000 millimeter. Its depth is 700 millimeter. The thickness of slab is 180 millimeter. And now we need to consider the section for the beam. For section of the beam, we need to calculate the distance from the soffit of slab up to the soffit of beam. So it is total 700 minus 180, so it will be equal to HB, so which is 520 millimeter. And 4 times HF times 4, to just consider this value, how much will be the projection or how much part of the slab need to be considered as beam. So 4 times HF, it comes to be 720. So 180 times 4, it is 720. Okay, and width BW for beam 1, which is 375. So 375. So this total value BW plus this HB are 4HF. So we will consider the smaller value out of HB and 4HF. So HB is 520 and 4HF is 720. So this 520 will be considered. So 520 plus 375. So it will be 890. It is 520 plus 375. HB plus width of the beam. Okay, so now we have the section, the dimension of section, then we can calculate the moment of area, second moment of area for beam. How we can do that? Now we have section like this. This is 375. This is 520. This is 180. And this total is 700. And this value, the governing value is 520, so it is 520. So based on this section, we can calculate I of beam. So if we want to do the exact calculation, so first we need to determine its centroid. So after determining the centroid, we need to calculate the second moment of area of this whole figure about this axis, about this centroid. So we can do the exact calculation, or otherwise we can estimate, or we can just assume that. So for simplification, we can do the estimation. How? If we calculate the area of this rectangular portion and then multiply with 1.5 to account for this portion. So it will give us a reasonable estimate for the second moment of area. Otherwise, we can do the exact calculation as well. So 1.5 times BH cube over 12, B is 375 and H is 700 cube divided by 12. So from here we can calculate the IB value. So it is approximate value. So IB value. Similarly, then next we need to calculate BS, width of slab. So for width of slab, first we need to consider the width. Which width should be considered? For B1, which is a edge beam, so if we go to this figure, so for edge beam, for this beam, this portion, if we cut the section from here, so this portion will be only considered as this much portion. So this is beam and this is slab. So from the center of the beam up to, or center of the column up to this centroidal axis, it is 6000 divided by 2, and plus we need to add this extension to consider the width up to half of this. And the width is again 375 divided by 2. So it will become 6000 divided by 2 plus 375 divided by 2. So 3187.5 millimeters. So it will be the width from the edge of the slab up to the center line. Here. So here this B will be equal to 3187.5. This L by 2, in case of B1, L by 2 will be its perpendicular dimension, which is 6000 divided by 2. So 3000, and this extension, this is equal to half of the width of column, which is 375 by 2, 187.5. So it will become 3187.5. So now we have width of the slab, then, and we also know the depth of slab. We can easily calculate the BS value. How? Now we have the section for the slab. This is 180 and this total width is 3000. Sorry. This is 3187.5. So IS will be equal to simply BH cube over 12, and here B is 3187.5 and H is 180 cube divided by 12. So here we can get the value of IS. So the value of IS is this one, and then take the ratio, because alpha F is equal to EC IB over EC IS. And if the material of beam and slab both are same, then the E value will be same. So we will left with only IB over IS. So their ratio will be this one, alpha F. So for B1, alpha F is 10.09. So this was the case for edge. Similar calculations will be for exterior beam B3. Only the span will be interchanged. In case of B2, which is an interior beam, again the span is, length is 8000 meter, H is 700, HF is, the thickness of slab is 180, HB is 520, 4HF is 720, BW, width of beam is 375, and B. For this, we need to consider HF from this side and HF from this side, and then this will be equal to HF or 4 times HF. So in this case, HF goes to 520, or here again 520 plus BW, this one. So this will give us the total value of BW. And again we can calculate the second moment of area for this T beam, because in case of interior beam it will be a T beam. So here we have the dimension 375, this is 520, this is also 520, this is 180, this dimension is again 520. So if we want to calculate the exact value of I, then first we need to locate its centroid and then calculate the moment of area, second moment of area of this shape about this centroid. We can consider this figure 1 and this figure 2, and we can calculate the second moment of area about this axis by using parallel axis theorem. Or otherwise, just for estimation, we can consider that it is 2 times the second moment of area of this beam, 2 times BH cube over 12. So 2 times B is 375 and H is here 700 cube divided by 12. So from here we can approximate the value of IB for interior beam. So here we will get the value of IB for interior beam. Similarly, we need to select the value of BS for interior slab or for the slab in case of interior beam. So in case of interior beam, the slab width will be from the center of the column or the center of that beam to the center of the next panel on one side and the center of panel on the other side. L by 2 on the right side and L by 2 on the left side. So again, if we go on the original picture, so here in case of this beam 2, we will have this much length. From here to here it will be L2 by 2 or 6000 divided by 2. Similarly on this side it will be 6000 divided by 2. So it will be equal to 6000. So this is also 6000 by 2, 6000 by 2, and again we will get the value for B to 6000. Okay, so once we have the value of B and the value of H, we have this value B and the value of H, so we can easily calculate by using BH cube over 12 the second moment of area of slab. So after calculating, just take their ratio, it is 6.38. Similarly, we can go for the exterior and interior beam in the north-south direction for beam 3 and B4. So after calculating the alpha F values for all these 4 beams, then take their ratio. So you take their average mean value. So their mean value is 5.31, which is greater than 2. So our assumption that the alpha F M value is greater than 2 is okay. Okay, next step is to check the limitations of direct design method. So the first limitation was there should be at least 3 span in both the directions. So in our case we have 3 span in north-south direction and 4 spans in east-west direction. So this limitation is okay. This is satisfied. And the second limitation is the panel should be a two-way panel. So their longer to shorter ratio should be less than 2. So it is 1.33. So our panels are two-way panels. So it is also okay. The third is the difference between the successive span lengths should be less than 1/3 of the longer span. So in our case, in each direction the spans are same, 8 meter, 8 meter and 6 meter, 6 meter. So the difference is 0. So this limitation is also okay. The third limitation was the ratio of live load to dead load should be less than 2. So in our case, the value of live load is given 300 kg per meter square and the value of superimposed dead load was also given 350. So we can also estimate the value of self weight of slab, which is 180 millimeter or 0.18 meter times the density of concrete, 2400 kg per meter cube. So from here we get the value 0.348, which is less than 2, so it is also okay. And in our case there is no concentrated load, so this limitation 4 is okay. So the fifth limitation was there should not be offset of column more than 10%. So in our case all the columns lie in the same line, so this fifth limitation is also okay. There is no offset. The sixth limitation is the alpha F ratio in direction 1. The alpha F or the average value of alpha F in direction 1 to the alpha F value in the direction 2, the ratio should be between 0.2 to 5. So in our case, if we take the ratio alpha F, so we need to take the average of alpha F for the beams in direction 1. So in our case, for panel 1, it is like this. Here we have B1, B2. So this is our direction 1, and B3 and B4. So this is our direction 2. So in direction 1 we have B1 and B2. So we will take the average of their alpha F. Similarly in second direction we will take the average of alpha F for B3 and B4. So their average, the flexural stiffness ratio comes out to be 2.28 for this panel 1, so which is between 0.2 and 5. So this limitation is also okay. So all the 6 limitations are okay. So it means we can use the direct design method to design this slab system, to design the given slab system. The next step is to decide the width of frame as well as the width of column strip and middle strip. For width of frame, simply we need to take the center line of the panel. So this will be our exterior frame and this will be our interior frame in case of north-south direction. So the width of exterior frame will be from center line of this column up to the frame, it is 4000 because the total is 8 meter. And plus we need to add this portion from here up to here. So it is 187.5. So 4187.5 is the width of exterior frame, and in case of interior frame its value will be 4000 here and 4000 here. It is 8000 or 8 meter. Similarly we can do for the east-west direction. And regarding the width of column strip, we know that the width of column strip is equal to L minimum divided by 4 for each panel, for exterior frame as well as for interior frame. So from the center line of this column up to here, this will be L minimum divided by 4. And in our case, in one direction the span is 8 meter and in the other direction span is 6 meters. So shorter span is 6 meter. So 6 divided by 4. So it will come 1.5 or 1500 millimeter. But for exterior frame, the slab is extended beyond the center line of this column. So we need to add this portion as well. So we need to add the half of width of column, which is 187.5. So the total width of the exterior frame, total width of column strip will become 1500 plus the half column width. So it is 1687.5 millimeter. So the width of half middle strip, it will be equal to the distance between the center line of the column up to the center line of the panel minus the width of this portion. So this total is 4000 we need to subtract this width 1500, so it will become 2500. So 2500 millimeter will be the width of half metal strip for exterior panel. Similarly, for interior panel, we also need to calculate these values. So for interior panel, again, this from center line of the column up to this much, it will be L minimum divided by 4, and on this side it is also L minimum divided by 4. And in our case, for both the side, on this side and on this side, the L minimum is 6 millimeter. The span, 6 millimeter span is the governing span. So 6 divided by 4, it is 1500 millimeter or 1.5 meters. So 1.5 meter on this side. So this will be the width of middle strip. So 1500, so it will be total 3000 millimeter, the width of column strip in case of interior frame. And if we talk about the width of middle strip in case of interior frame, so again from the center line of the panel up to the center line of the column, the total distance is 4000 millimeter, and we need to subtract this much width, which is 1500 millimeter. So it will come out to be 2500 millimeter. So in the same manner, we can also calculate the width of column strip and middle strip in the east-west direction. Again, the rule will be the width of the column strip should be L minimum by 4, and the remaining portion from the center line of the column up to the center line of the panel will be the width of middle strip. Okay, after deciding the width of column strip and middle strip, the next step is to calculate the static moment for each frame. We have seen that the static moment, which is equal to WL square over 8 in case of beam, and similar is the case in case of slab having width L2W or L2, width of frame or width of design strip. Okay, here WU is uniformly distributed load, L2W is width of frame, and Ln is clear span. So first of all, we need to calculate this WU. For WU, which is factored load, so first we need to calculate the dead load. So superimposed dead load is given 350. We need to add the self weight. So 0.18 times density. So it is 782 kilogram per meter square. So we need to factor for dead load 1.2 factor and for live load 1.6 factor. And this unit is in kilogram. So we need to convert it into kilonewton. So it is a mistake. It should be a kilonewton per meter square. So once we have W, so we can go for this table. We can make a table to calculate the static moment. For example, for east-west direction for exterior frame. So in east-west direction, the span is 8000 meters. So L is 8000 millimeter. L2W, so which will be a perpendicular dimension from this, which is 6 meter or 6000 millimeter. And for exterior frame, the span will be half. The width will be half of the frame plus the half of the column width, as we have seen in the previous slide, that we need to consider for exterior frame. Here we have a column, here we have a column. So this is the center line of the panel. So this total is from this center line up to this center line. This total distance is 6 meter and this is 3 meter. So this one 3 meter or 3000 millimeter, plus we need to add this portion, which is 375 divided by 2, 187.5. So total width of frame for exterior frame is 3187.5 millimeter. So here the L2W is 3.188 or 3188 or 3187.5 millimeter. And Ln is clear span. So again, for clear span, we need to check. Here we have a column and here we have a column. And the distance from the center of this column is 8 meter. So 187.5, half of the column width from this side and half of the column width 187.51. This side we need to subtract this to get this clear span. So it will become 8000 minus 375. So from here we can get the clear span value. So clear span value is 7.625 millimeter or 7625 millimeter. So now we have this ln value, L2W value and WU value. So we need to simply substitute these values in this formula to get m naught. So here the m naught is static moment is 322.3 kilonewton for exterior frame in east-west direction. Similarly, we can go for interior frame, only the difference will be the L2W value. So this one is same, this is different, this is same. So the only difference will be this one. Similarly, we can also go for north-south direction. Here the span is 6000, and for exterior frame, the width will be 4.188 millimeter, and for interior frame it will be 8 millimeter. Because when we are considering this north-south direction, up to the center line of the column and up to the center line. So here this distance is 8 meter. So the frame width will be up to the center line. So this one is 4 meter, and for interior frame it will be 4 plus 4. So here 4 plus this 187, and for interior 4 plus 4. So 4.187 and 8 meter. So only the difference is this one in case of east-west and north-south direction. Similarly, ln clear span will also be changed because in this case we need to subtract the width of column from 6000 millimeter or 6 meter span. So after getting these three values, we can substitute in the formula to calculate the static moment value. Okay, once we have calculated the static moment value, the next step is to distribute that static moment in longitudinal direction, in transverse direction and in vertical direction. So first of all, the distribution in longitudinal direction. To distribute that moment in longitudinal direction, for example, if I talk about this direction, east-west direction, so we have calculated m naught, the static moment maximum. But here in actual, the moment will not be 0 at this end and at this end. So its distribution will be somewhat like this. Here negative, at the center positive, and here negative. So we need to distribute. So for first of all, we consider for exterior panel. So for exterior panel, we need to select the coefficient for exterior negative moment, positive moment, and interior negative moment. And their distribution is based on the end conditions. So here if we see, we have beams all along this panel. So on all four sides we have the beams. So we need to consider the suitable case from this table. So the first is exterior edge unrestrained, and there is no beam, there is no restraint between the slab as well as the supporting member. Slab with beams between all supports. So this second case will be a governing case in our case. So at interior support we will have a negative moment which is 0.7 times m naught, positive moment will be 0.57 m naught, and exterior negative moment will be 0.16. So we have selected these values, so I have written these values over here. So m naught at exterior support is 0.16 m naught, middle support positive moment is 0.57 m naught, and m negative is 0.70 m naught. So it will be like this. At exterior support in this direction it is continuous. So here 0.16, 0.57 and 0.7 over here. So let's consider for the exterior and interior frames in both the direction east-west and north-south direction. So I have made a table over here. So in this table, first we consider east-west direction, and for east-west direction again for the exterior frame. So we have already calculated the static moment value for exterior frame in east-west direction, which is 322.3 kilonewton meter. So we can go there and check. For exterior frame, we have calculated this value 322.3 kilonewton meter, and for interior frame it is 606.7 kilonewton meter in east-west direction. So we need to select these values, or we need to reproduce these values in the first row, and then we need to calculate the negative moment at exterior support, positive moment at mid span, and then m negative at the interior support based on these selected factors. So we just need to multiply the corresponding m naught with these factors to get the corresponding value. For example, for m negative at exterior support, what we will do, we will multiply this 322.3 with 0.7. 1.16 to get this value. When we will multiply this with 1.6, so the value will be 51.6. It means at exterior support in east-west direction, the moment will be 51.6 kilonewton at the face of this column. The negative moment will be at the face of the column. Similarly, we can go for the positive moment. So for this value, we need to multiply 322.3 with 0.57, and for this value we need to multiply 322.3 with 0.7. So in this way we can calculate these values. Just we need to multiply these corresponding moments with the selected coefficients. Okay, so from here our longitudinal distribution of static moment will be complete. So we have calculated the static moment. We have calculated the positive and negative moment at different locations. If I place on this figure, so it will be at this position, and at this position for exterior frame, and for interior frame it will be here, here and here. So this is the longitudinal distribution of static moment. So the next step will be to distribute this calculated moment in the transverse direction, in this direction, to column strip and middle strip. And for here this column strip and middle strip. So we need to distribute this moment in the transverse direction. So for that, when we are distributing or finding the coefficients for the distribution of positive and negative moments in transverse direction, we need three factors or three parameters. The first one is alpha f for the beams in the direction of the span. So we need their alpha f value. And we also need the aspect ratio of the panel, L2 over L1. And similarly, we also need the torsional coefficient or the torsional stiffness ratio, beta t. So to calculate the beta t, first we need this C value. So here, we need to calculate beta t, because we have already calculated the alpha f value just after selecting the thickness of slab, but the beta t value is not calculated before. So we need to calculate this value. So for beta t, we see the formula. It is elastic modulus of concrete for beam times C, which is torsional coefficient, torsional constant, and then 2 times ES, which is elastic modulus of slab, times IS, second moment of area of slab. So EC and ES are ECB over ECS. It is same, so it will cancel out. So we will only left with C over 2 times IS. So we need to calculate this factor C for the edge beams. So in our case, if we see this panel 1, this is our first panel. So in this panel we have this beam B1 and B3. So these two are edge beams. So we need to calculate the beta t value for these two edge beams. So first we will calculate the torsional constant for these two beams. So for B1 and for B3. So to calculate the torsional constant for these B1 and B3, we need to first find the shape of, or find the dimension of the edge beam, and then we will consider these two cases, case 1 and case 2. Again, for the dimension of this edge beam, we can select like this. For example, if I talk about the B1, so it is 375 millimeter, and here its total depth is 700 millimeter, and the thickness of slab is 180 millimeter. Then we need to calculate this value HB, which we have already calculated, which is 520 millimeter. So this value from here up to here, it will be either 520 or 180 times 4. So if we compare 4 times 180 or 520, so this 520 will be a lesser value, so this value will be 520. So these will be the dimensions of our beam, edge beam. So now we can convert this edge beam into two shapes like this, shape 1 and shape 2, or otherwise we can have a second option like this. This is shape 1 and this is shape 2. So for these two cases, we need to calculate the C value, and then we will consider the larger value as a torsional constant. So here when we will divide these figures into 1 and 2, the shorter dimension will be termed as x and the longer dimension will be termed as y. So for figure 1 it will be x1 and y1, and here this will be x2 and this one will be y2. Similarly for this figure, this will be x1, this will be y1, and this will be x2 and this will be y2. So larger will be termed as y and the smaller dimension will be termed as x. So we have decided the shape, so we will consider for these two cases. Case 1 this distribution, and for case 2 this distribution of H beam. So I will solve for case 1 for beam 1. The similar procedure will be for the next 3 cases. So first of all for case 1. So here it is beam B1. BW is width of beam is 375, so this dimension is 375. HB, this dimension is 520. This X1, which is width of, so depth of slab, which is 180. So Y1, if this is the figure 1, so Y1 will be 520 plus 375, so it will be 895. So this is 520 plus 375, this total length. And X2 for this figure, this is 375, and Y2 is equal to HB, which is 520. So we need to substitute this X1, Y1, X2, Y2 value in this C. So we can substitute, or we can calculate it like this. C is equal to 1 minus 0.63 x1 over y1 into x square y over 3. So this will be for shape 1, and in each figure or for each beam we have 2 shapes, so we will also add for the second one, which is 1 minus 0.63 x2 over y2 times x2 square y divided by 3. So by substituting these values, the corresponding values of x1 and y1, we can get the value of C. So after substituting, the value of C is for case 1 is this one, and for case 2, if we consider this figure, so it is this one. So we will consider the larger values out of these two. This second value is the larger one. So similarly we can calculate for beam 3. So once we have calculated the C value for B1 and B3, next we need to check, or we need to calculate the beta T value. So to calculate the beta T value, it is very important to understand that for which case, which beam will be considered as a edge beam. For example, for this frame, for this interior frame, in this direction, the beam perpendicular to this one, this will be considered as a edge beam. So in east-west direction, when we are considering east-west direction, B3 will be the edge beam. So in east-west direction, the edge beam is B3. Similarly, if we consider this span, so in that case, the perpendicular beam will be the edge beam. So B1 will be the edge beam in case of north-south direction. This is very important to understand. Okay, so again I have made the table. We need to substitute the values. So for east-west direction, we have B3 and B3 in case of exterior and interior frames as the edge beam. So their C value we have already calculated, which is 347423. And then we also need to consider this BS value. So BS, the width of slab, is actually equal to the span length of the torsional edge member. So torsional edge member means this edge beam. So whatsoever is the span of the edge beam, the same will be the width BS. So if we talk about this B3, so its span is from the center line of this column up to this one, it is 6 meter. So 6 meter will be the width of slab that will be considered to calculate the torsional stiffness ratio. Okay, so once we have this B value, and we also have H value and B value, so we can easily calculate BH cube over 12 as a second moment of area. So we have second moment of area. Now we need to just take the ratio by using this C over 2IS. So it comes out to be 0.5957 for B3 in east-west direction. Similarly, we can also do the calculations for north-south direction. Okay, now we have all these three factors, alpha, aspect ratio as well as beta t. So now we can proceed for the moment distribution in the lateral direction. For moment distribution in the lateral direction, we have two options. Either we use these tables to select the values for the contribution or the portion of interior moments, interior positive, negative, as well as exterior negative moment to the column strip, or otherwise we can use these equations to calculate the percentage of column strip out of the positive negative moments that we have find or determined by using longitudinal distribution. So for example, here I use these equations. If we use these equations, so it will become easy because we don't need to interpolate the values. But in case of these tables, we need to interpolate the values corresponding to the alpha f value, aspect ratio, as well as for beta value. So better is to use this equation. So for these equations, we don't need any interpolation. So in these equations, we have three parameters, D, A, and B. So A is aspect ratio L2 over L1. So this is the ratio of spans of any panel. So in case of panel 1, it is 6 over 8. Alpha F is the flexural stiffness ratio of beam. So in case of exterior frame, we are considering beam 1, exterior beam B1. So we will consider there its alpha F value. Similarly, for interior frame, the beam will be B2. So for B2, we will consider the corresponding value. So we have already calculated these values in the table just after selecting the thickness of slab. So we just need to understand that for exterior frame, if we are considering the exterior frame, in that case, for example, I consider east-west direction. So this is exterior frame, this is center line. So in that case, the beam B1 will be the beam which is in the direction of span or in the direction of reinforcement which we are going to calculate. So this will act as a flexural member, so we need to consider this B1. And the beam perpendicular to this one, which is B3, that will be considered as a torsional member. So flexural member B1, so we consider its alpha F value, and B3 we will consider its beta T value. So the selected value or the selected value of alpha F, here it will be for B1, here it will be for B2, and for north-south direction this will be for B3 and this will be for B4, these values. And then we need to calculate this D, which is alpha F L2 over L1. So if the value of this factor is greater than 1, then we need to consider it as equal to 1. So in all these four cases, its value comes out to be 1. So the D value is 1 for all the four cases here. So the next is beta which is equal to B, which is equal to beta T, and it should be less than 2.5. So again we need to consider that which beam will be considered as the edge beam. So in case of east-west direction, beta beam 3 will be considered as edge beam for these two cases, and for north-south direction B1 will be considered as a edge beam for these two cases. And all these values are less than 2.5, so we will consider the actual values. If this value is more than 2.5, then we need to consider it equal to 2.5. So now we have A, D and B, so we just need to substitute in these equations, three equations, to calculate the percentage of moments in the column strip. So first of all, percentage of MD positive to column strip. What it means, how much moment will be resisted by the column strip out of MD positive, middle positive moment. So the middle positive moment, we have this first formula, percentage of MD positive to column strip, 60 plus 15 times 3.3 minus 2A into D. So when we will substitute these values, so this percentage comes out to be 82.5. So it means out of this MD positive, 82.5% will be resisted by the column strip, and the remaining 17.5% will be resisted by the middle strip. So 82.5% for column strip from this equation, and the remaining 17.5 is for middle strip positive moment. Similarly, we need to calculate this value for interior negative and exterior negative. For interior negative, we will use this second formula. Again, when we substitute these values, value of A and D, it comes out to be 82.5. So it means out of M interior negative, 82.5% movement will be resisted by column strip, and the remaining 17.5 will be resisted by the middle strip. So similarly for exterior negative movements, so we will use this one here. This B value will be included as well. So when we substitute the value, it comes out to be 95.83. So it means 95.83% will be resisted by column strip, and the remaining 4.17% will be resisted by the middle strip. So for middle strip, we just need to take 100% minus the percentage of column strip. 100 minus percentage of column strip. So it will give us the percentage of moment resisted by the middle strip. Okay, next, in the previous table we just have calculated the percentage, but we need to calculate the actual moment values. So I have reproduced that table over here, the percentage of middle strip, percentage of column strip, 82, 17.5, 82, 17.5, 95.83 and 4.17. So I have just reproduced that table over here just as a reference. So now we need to calculate, instead of percentage, the actual value of MD positive to column strip. So what we will do, so we will first consider what is the value of M positive at midspan for east-west direction for exterior frame. So we have already calculated this value 183.7. So we can again check. Here we have calculated in the lateral distribution. Sorry, not here. In this table. So M positive, east-west direction, exterior frame, it is 183.7, and for interior frame it will be 345.8. Similarly for M negative at interior spot, it will be 22.25 and 424. So we can recheck these values over there. So if we check again, this MD value is 183, 345 and 225.51. So we have seen that in the previous table. So now we need to distribute this 183.7 to column strip and middle strip. And we have seen that we have selected the coefficient that the contribution of column strip to resist this MD positive will be 82.5%. So 82.5% of this movement will be resisted by the column strip. So what we need to do, 82.5 divided by 100 to convert into fraction, multiplied by 183.7. So when we will do this, we will do the calculation, so it will come out to be 151.55 kilonewton meter. So what it means, out of 183.7 kilonewton meter moment, 151.5 kilonewton meter moment will be resisted by the column strip, and the remaining moment will be resisted by the middle strip. So we can calculate this value 32 in two ways. Either subtract 183.7 minus 151.5, so it will give you 32.15 kilonewton, or otherwise we have seen that the percentage is 17.5, so 0.175 times 183.7. So either way we can calculate the contribution of middle strip to resist this MD positive. Okay. Similarly, we can do the calculations for negative moments at interior spot. So the total moment is this one. It's 82.5 will be resisted by the column strip. So we just need to multiply this value with 0.825. And if we multiply this value with the 17.5 or 0.175, it will be the contribution of middle strip. Similar procedure will be for exterior negative. We just need to consider these percentages and multiply it with the total moments to get the moment at middle strip and column strip. So this is the lateral distribution of moment, distribution of moment to column strip and middle strip. So now we have decided how much will be the moment at column strip and middle strip. So the next is vertical distribution. What it means, we have considered the middle column strip. So if we see the column strip, it constitutes of beam as well as slab. So this will be the section of a column strip. So in column strip, some moment will be resisted by this beam and some moment will be resisted by this portion of the slab. So the question is, how much will be resisted by this beam and how much will be resisted by these slabs, column strip slabs. So for that we need to see the vertical distribution. Again, either we can use this table given in the SEI code, or we can use this equation to calculate the percentage of beam, percentage share of beam from the column strip moment. For example, if we use this formula, so we need this D, which is alpha F L2 over L1, and we have already calculated this is equal to 1 for all the cases. So if this is 1, so the contribution of beam will be 85%. So percentage share of beam from column strip is 85, 85, 85 for all the column strips, and the remaining 15% will be resisted by the column strip slab. Beam will resist 85% and slab will resist 15%. Okay, so once we have these percentages, so we can now convert the column strip moment to column strip slab moment and beam moment. So here in this table I have mentioned the lateral distribution. So we have the column strip moment for east-west direction exterior frame 151.55. So we can verify this. For positive moment, column strip moment is 151.55. So go over here. So the share of beam from this column strip moment. So out of this column strip moment, 85% will be resisted by the beam. So we need to multiply this factor with 0.85. So 0.85 times 151.55. So it will be 128.81 kilonewton meter. So this much moment will be resisted by the beam, and the remaining will be resisted by the 22.74. Either we can go 151 times 0.15, or we can do 151.5 minus 128.8. So in both the ways we can calculate the contribution of column strip slab. The similar procedure can be adopted for the interior negative and exterior negative, and for north-south direction interior and exterior frame. So this is vertical distribution of moment. So now we can combine all these distribution, lateral, the results of lateral distribution as well as vertical distribution. So we have this moment MD positive. So we have calculated its part, which will be resisted by the column strip, and this column strip moment will be further subdivided into beam as well as slab. So this 151 is distributed further into two parts: column strip moment and beam moment and column strip slab moment. So this is beam portion 128, this 22 is slab portion from column strip, and this third one is 32.15. So if we add these three moments, it will be equal to this, this one 150, no sorry, it will be equal to 183. So the M positive total will be equal to middle strip moment plus column strip slab moment plus beam moment. So it will be sum of these three. So the final distribution or the final results which are required are actually these three, because if I draw the section, it is like this. Here we have beam, for example I draw for the interior span or interior frame. So interior frame is like this. Up to here, and here we have this much middle strip, half middle strip, half middle strip on this side, and this is our beam, and this is half column strip slab, half column strip slab. So this moment 128.81 will be resisted by this, the 8.81 will be resisted by the beam, and this 22.74 will be resisted by this slab one, total 22.74, and these two half middle strips will resist only 32.15. And if we want to calculate the parts resisted by this half middle strip and this half middle strip, then we need to distribute this middle strip moment proportionally to these half middle strip. If their width are same, then it will be simply half, otherwise we need to proportionally distribute. and how we can proportionally distribute I have discussed in the previous video. So similarly, this was for positive moment. The similar procedure will be for interior negative moment. So we will distribute this interior negative moment to first column strip moment, then this column strip moment will be distributed into column strip slab and beam moment, and then this moment will be distributed into this one negative middle strip moment. So we will again have middle strip moment, column strip slab moment, and beam moment. Column strip, the beam within the column strip, the moment resisted by the beam which is within the column strip. So similarly for exterior negative moment, and we need to do this calculation for all the frames, interior frame in east-west direction, exterior and interior frame in north-south direction. So once we will distribute this moment, so after that we will have moment all along or at all critical points of our panel 1. Okay, for example, I can show you where these moments will lie. For example, this is our panel like this. So here this is half. Now I can change if this is visible. So I show in the north-south direction, for east-west direction. So up to here we have, this one is column strip, this one is total middle strip, and this is half column strip, and then again here will be half column strip. So our moments will be for column strip moment, we will have just moment for this portion. This is our column strip slab. So we will have moment at this location at the face of the column, which will be exterior negative moment at column strip. Similarly, we will have moment at this location, exterior negative moment at column strip slab. Similarly, for middle strip, we will have moment at this portion, and for column strip, we also have this positive moment here. We will also have moment over here and moment at this location. So similarly, this will be from this frame, exterior frame. We will also have moment from interior frame. So we will have the values 1, 2, 3, 1, 2, 3, and 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we will have 12 different values in one direction at 12 different locations. So if we see, in one direction we have values 1. No, not for this beam, because we are going to design only slab. So we will consider 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these 12 values will be placed or reported for the slab in one direction. Similarly, 12 values will be for slab panel in the north-south direction. So for these 24 values of bending moment, we need to calculate the area of steel. So once we calculate the area of steel for these 24 values, then we will select the spacing as well as the number of bars or diameter of bar. So the next step is steel calculation. We need to calculate the steel for column strip slab and middle strip slab. So to calculate the steel reinforcement, we can use the same concept as we have used for singly reinforced beam, tension controlled singly reinforced beam. So for that, we can use this equation for reinforcement ratio. So in this equation, W is 0.85 Fc prime over Fy, R is Mu over Bd square. So we just need to substitute these values to calculate raw value. But here we also have this effective span or effective depth of reinforcement in north-south direction and east-west direction. So first we need to decide in which direction we will provide the reinforcement first. For example, if this is our panel, so we provide the reinforcement in this direction, in north-south direction first, and then we provide the reinforcement in this direction. I am talking about the bottom reinforcement, and if I draw its section, it will be like this. So first I have placed this reinforcement, bottom reinforcement in this direction. Sorry, I consider this reinforcement first, So it will be, sorry, for example, I provide this reinforcement first in this direction and this reinforcement at the later stage are after the first reinforcements. And if I draw its sections, it will be first at bottom this reinforcement will come and then this reinforcement will be above that bar. So if I calculate the effective depth, so effective depth in this direction, which is east-west direction, it will be up to the centroid of this bar, and in north-south direction it will be from here up to the centroid of this bar. So here we have considered that this north-south reinforcement is provided first as it is a shorter span. So we have total depth 180, 20 millimeter is clear cover. So 7.5 we are considering that the diameter of the bar is 13 millimeter or 13.5 millimeter. So we will subtract the half diameter of bar. So in north-south direction or for north-south direction reinforcement, the value is 152.5. This is for bottom reinforcement. Similarly for east-west direction, we will subtract 20 millimeter from 180 as a clear cover, 13.5 millimeter the diameter of bottom bar, and 7.5 the diameter of upper bar. So it will be like this actually. This is our bottom bar and this is upper bar. So for bottom north-south direction it is 180 minus 20 minus half of this dia, 13.5 divided by 2. And if I calculate for this one, so in that case it will be 180 minus 20 minus dia of this bar, complete dia of this bar which is 13.5 minus dia of half dia of this bar, 13.5 divided by 2. So in this way we can calculate the effective depth in both directions. This is for bottom. Similar will be the case for top reinforcement. For top reinforcement it will be just opposite. Here we have reinforcement in one direction and in the second direction. So now it will be made from the bottom. So these values will remain almost same. Okay, so now we have this effective depth in both the direction. So now we need to calculate the reinforcement ratio from the calculated bending moments. So first we consider the column strip. So for column strip, if we see the width of column strip, we have already calculated the width of column strip, which is actually this one. For interior frame we have calculated it was 1500 and 1500, but here we have this beam as well. So this out of this column strip, the slab portion is only this one. So if I talk about the width of half column strip, it will be equal to, this one is 1500, so 1500 minus half of this beam width, and the beam width is how much in east-west direction if I talk. So the B1 width is 375, so 375 divided by 2. So this will be the width in east-west direction. So we have calculated, so width in east-west direction is 13 or 1.313 meter. So width of half column strip in east-west direction. Okay, we have calculated the D value for east-west direction, which is 139. We know the moment value for half column strip, because in exterior frame the column strip width is only half, so it will remain same, but for interior frame we need to half this value, because as I have made the diagram over here, so this is, if this is the beam, so this is half column strip and half column strip, and we have calculated the moment for both of this for complete column strip. So for this one we need to divide it by 2. For interior frames we need to divide it by 2, and for exterior frame it is already a half column strip. So now we have moment D as well as total width B. So we can calculate this R value, W, and reinforcement ratio rho. So once we have reinforcement ratio, so based on this B and D we can calculate the area, so which is 414, and then from this area we can select the number of bars. So if we use 6 bars of 10 millimeter dia, so in that case the area of this bar will be more than 440 1 millimeter square. So we can use 6 number 10 bars. Similarly, we can also calculate the number of bars for other locations. For interior frame, half column strip movement, we will calculate. So all those 12 locations that I have identified in east-west direction, we will calculate the reinforcement ratio for those 12 points or 12 locations. Similarly, in north-south direction, we will also calculate the reinforcement ratio or number of bars for those 12 locations. So after calculating the number of bars for those, I have left some calculations just for you, and I have assumed these values. So these values are assumed values. I didn't perform the calculation. So you can perform by yourself. By using Excel sheet, you can do this calculation very easily. So once we have this value, this is for half column strip. Similarly, we can also calculate for half middle strip. And again for half middle strip, for exterior frame, the half middle strip width is 1500, and for interior frame it was also 1500. So we have already seen that. So once we have the width and we have depth value, effective depth value, and the moment value, we can calculate the area as well as the number of bars. So after calculating the number of bar, finding the reinforcement, we need to do the detailing. We need to communicate this design. So here I will show just for one direction. We have calculated that, for example, in north-south direction, I have highlighted these values with the red. North-south direction, first of all, is M positive, middle positive, and for that the bars are for column strip 4 number 10 bars. So let's see how we will locate for interior frame as well as for exterior frame. How we will locate this positive reinforcement in north-south direction for column strip. So it is for column strip and positive reinforcement. So here is the column strip. So this is column strip, and this reinforcement shown with the blue line, it is the positive reinforcement. So 4 number 10 bars. So these will be distributed in this much width, half column width. So not this much width, sorry, it will be up to the face of the beam, because this is for slab only, not for the beam. So we need to just provide up to the face of the beam. So this is a mistake over here. Similarly, on this side it will be up to this much length, not this one, it will be up to this one, from here up to here. So we need to provide 4 bars of 10 millimeter dia in this portion. And the next question, how much we need to extend this reinforcement? If we talk about this extension, I have started from this support or from the edge of the beam. Will just leave the minimum cover, which may be 20 millimeter, and then I have extended it throughout up to the next support. Similarly on this side. So how do I know that? So for that we need to check the code guidelines. So if I check the code guidelines, I have placed a chart over here for column strip bottom reinforcement, because M reinforcement corresponding to M positive, it is a bottom reinforcement. So we need to extend throughout all the 100% reinforcement. So that's why I have extended this reinforcement throughout the length, throughout the span. I haven't curtailed these bars. Okay, similarly, I check for the negative moment. So first I check for the M positive. Now I check, for example, M interior negative. So for M interior negative moment at the interior support, we have the 5 number of bars of 10 millimeter dia, 5 number of bars for 10 millimeter dia for interior as well as for exterior frame in north-south direction. Interior negative moment. So let's see how we will look at that. So in north-south direction, interior negative moment will be at these spots, at the face of these spots. And again we have 5 number of bar, 5 number of bar. And we need to provide this from this point up to the face of this spot. So it's my mistake that I have shown up to the center line of these columns. It should not be like that. It should be up to the face of the beam. So we need to provide 5 bars in this much length. 5 bars in this much length up to the face. And next question is, how much will be their extension? So it is a negative reinforcement. So negative reinforcement I have shown with the red color and dotted lines. So negative reinforcement will be a dotted line. So the question is, how much I need to extend this from this face in this direction and from this face in this direction. How much will be extension? So again, we need to go to the design guidelines or the code guidelines. So column strip and top negative reinforcement. 50% will be extended up to 0.3 ln from the face of the support, and the 50% or the remaining 50% will be extended 0.3 ln from the face of the support. So same I have done. I have extended the alternative bar. So the one bar is 0.3 ln. ln is the clear span from here up to here. It's 0.3 times. I have extended this bar, and the other bar is extended 0.2 times ln. Similarly on the other side of the support. So this is how we place this negative reinforcement. Similarly, we will place the reinforcement for exterior negative moment at column strip. Similarly, we will place the negative reinforcement for middle strip. For example, I check one for middle strip. So this is for middle strip. For example, M positive for middle strip. So in north-south direction, it is 12 bars, number 10, 12 bars, number 10. For exterior, it is 12, and for interior, it is 12. So let's see how we will place that. So here given is, from here up to here, we have middle strip for exterior frame, and from here to here we have middle strip for interior frame. For exterior frame we have 12 bars, and for interior frame we have 12 bars. So this slab is continuous, so we can combine it. So I have combined this portion and I have taken it as a cumulative. So from here up to here it is total middle strip, and the total number of bars will become 24. So 24 bars will be positive reinforcement. 24 bars of 10 millimeter dia, and we need to provide for this much width, for this width of middle strip. And in this direction it is, I think, I don't exactly remember the width, so it will be like this. So we have calculated this width already. Okay, now question is, how much I need to extend? So here I have extended one bar throughout, and I have curtailed one bar on one direction, but at the exterior support I haven't curtailed that bar. So again I have followed the guideline of the code. So here if we see for middle strip, its bottom reinforcement 50% should be extended throughout, and 50% we can curtail at a distance 0.15 ln. So I have curtailed at a distance 0.5 ln from the face of the support. It should be from the face of the support like this. I need to curtail it over here. So this much distance from here up to the face of the support, it will be 0.5 ln, and ln will be, span will be this much, clear span from here to here. So in this way we can detail our slab. After calculating the moment at different locations, we need to calculate the reinforcement area, then we can show on the reinforcement panel in one direction, in north-south direction, as well as in east-west direction. So either show the reinforcement of both direction on a single drawing, or we can also go for the separate drawing as well. So this is all about this design example. So in this example we have seen how we can use the direct design method to design a two-way slab system, how we can distribute the moment, how we can calculate the reinforcement, and then place in or locate or detail the reinforcement for the slab. In the next video we will cover the design for shear